Hey, welcome back, goons and gamers. We are going to talk about ellipses today. So this will be halfway done with conic sections, I think. Yeah, halfway. You've already learned 2. There's only 2 left. So, technically one more, but I don't think we're gonna learn that conic section. I'll tell you what it is later. But yeah, so we're on ellipses. So what you are going to learn today is you're going to figure out how to find the center of an ellipse and the radius of the minor and major axes. We'll talk about the minor and major axes in a second, but basically an ellipse is just an oval. That's a terrible oval, but we'll pretend it's a good oval. So you're going to find... Never mind, I already don't like this oval. Oh well. Okay, so you're going to be able to find... Yeah, that's a little better. A little flat, though. The minor and major axes. So minor is just the smaller, right? Small things are minor problems. Major problems are big problems. So you're going to be able to figure out what's the narrowest your oval ever gets and how long does your oval get, and then where is the dead center of that oval. Cool? And that's all you have to do. Unfortunately, if we weren't in a pandemic, if someone had taken precautionary steps to help prevent the deaths of 200,000 Americans, and, we could sit together in the same room and breathe the same low quality air together, then we'd learn about focuses, we graph these ourselves, we do all sorts of exciting things. I might even show you how to do the construction for an ellipse. That would be tight, huh? But unfortunately, we have to sit at home, breathe our own home air, no sharing air whatsoever, and we've got to, just make do. So we'll focus on the center and then the minor and major axes, and then maybe someday we'll worry about cool stuff like foci and constructions and stuff. But for now, centers and axes is what we got. So let's start with the definition of an ellipse, or maybe how we get them. So we've talked about circles, which is we cut directly across our cone and then we get a nice little circle. Parabolas, we put a plane that cuts our cone that is parallel to one edge so that it never flies out the other side. But if we tilt this a little bit so that it does come out the other side, what ends up happening is our parabola closes off and then we get an oval. Exciting, right? So we've got the ellipse by slicing diagonally through one of the cones, making sure we come out the other side. So there are 2 different equations. In my mind, there's only one equation, but I'm not the guy who writes math textbooks. So we'll go with what everyone else says, but all right, maybe I'm just complaining at this point. So let's talk about these 2 equations. Ignore this for right now. We'll come back to that. Don't look at that. All right. So we have x minus h squared over a squared plus y minus k squared over b squared equals 1. So this is actually super, super similar to a circle, right? Our circle is x minus h squared plus y minus k squared equals r squared. So we still have that x minus h squared. We still have the plus sign in the middle. We still have the y minus k squared. And our r squared turned into a 1 somehow. So what's going on with this is because an ellipse has a minor and a major axis, it kind of has 2 radii. It has a long radius and it's got this little short radius, right? So we can't capture the full essence of an ellipse in a single radius number. So what we do for an ellipse is you actually have 2 radii numbers. They are the A and the B. The A tells us the major axis. So this distance here, from the center of your ellipse to the longest or furthest point, this distance is A. So just like we have r squared, we have a squared. And I'll give you a guess. Go ahead. Take a second. Turn to your dog. Tell them what do you think B is? Just go ahead. Tell Pablo the dog what you think B is. Oh, I knew it. You guys are geniuses. It's the minor axis. Oh my gosh. It's like I don't even have to teach you guys. You're just so smart. Actually, you're hard workers. You're not smart. You got this far because of diligence and hard work. So B, not B squared. Right, the formula is B squared. But here, B is the distance from the center of your ellipse to the closest point. This is called your minor axis. Or technically semi. What? All right, and semi just means that we're not looking at that full diameter. We're looking at the radius. Semi means like half, so it's half of the full axis, but it's a radius, right? So there you go. H and K are still the same things. This is your horizontal shift. This is your vertical shift. This is your major axis radius. This is your minor axis radius. And then because we've broken our R into two different things, they're over here now, and then this is always just a 1. Cool. Now you're going to say, Barton, what about that equation down there that you scribbled out? So let's go peek at that. Well, we still have y minus k squared. We still have x minus h squared. We still have a plus in the middle, but these things have swapped positions. So the reason for that is because now the a is under the y's binomial and the b is under the x binomial. We're going to go on to the next slide, and we're going to look at what does that even do for us. So I just need a little bit of room to draw here. So A is your semi-major axis every single time, and B is your semi-minor axis every single time. So this, whatever number is underneath the x term, that is always connected to the horizontal width of your ellipse. And B, or not B, excuse me, not B. Well, in this case B, but not always B, as we can see over here, right? Whatever is underneath your y is always the vertical size of your ellipse. So if we graph this one, because we have an A under the x term, and A is always your semi-major axis, all that's telling us is that we have a wide ellipse. It's wider than it is tall. It's like Dudley from Harry Potter. Okay? If we swap these, I've swapped the tops here. You could also swap the bottom. So you could turn this into a b squared and this into an a squared. Either one, they're equivalent, right? Because addition is commutative. I've swapped the tops here. If you have the major axis under your y term, the only difference that makes for our graph is it makes the vertical for our oval longer than the horizontal. So something you want to know, A is always greater than or equal to B, because if it's the longer axis, the radius has to be bigger. If they're the same, that's actually kind of a special case. If A equals B, then your two axes are the same width, and then you get a circle. So circles are special ellipses, sort of. It's kind of like squares are special rectangles. Circles are special ellipses. So the only difference here is if A is under the y term, that means we have a tall, skinny ellipse. If A is under our x binomial, we have a fat, short ellipse. All right, and I'll go ahead and make the joke now since we're not in class and you guys can't be self-deprecating. But just know, one of your classmates is going, my semi-major axis is under the x, and they're calling themselves short and fat. And then like 3 other kids go, same girl. And it's always a girl who does it for some reason. Maybe not. Maybe I'm being sexist. All right, we'll say boys do it too sometimes, but I feel you either way. Being short and fat. Just say that your semi-major axis is a little bit longer. Say your semi-major axis is oriented horizontally. That's way better than saying you're short and fat. All right. So short story long. If A is under the X, you have a wide ellipse. If A is under the Y, you have a tall ellipse. And that's the difference between those two equations. Cool. All right. So we've talked about these equations. We've talked about how H is our horizontal shift, K is our vertical shift, A's the long axis, B's the short axis. Whatever's under the X tells you how wide stuff is. Whatever's under the Y tells you how tall your ellipse is. So now that we've kind of broken down the equation, investigated a couple pieces of it, let's go ahead and look at a couple of examples that are going to be similar to your homework. That way when you do your homework, you don't cry and freak out. So example 1. Find the center, the semi-major axis, and the semi-minor axis of the following equation. So here's our beautiful ellipse equation, and it's even in the nice form. And you go, wait a second, Barton. Nice form? You only showed us one form. I know. Foreshadowing. Whoops, I can't spell. All right, good thing I'm not an English teacher. This equation makes it very easy for us to find these three critical components to our ellipse. So our center is at HK, just like the vertex and the center of every other equation you've ever found in your entire math career. So H is the number inside the binomial with the X, but because it's inside a math operation, remember the sign is flipped. Because we see a -6 here, H equals +6. And then K is the number inside the parentheses with the Y, but again, it's inside of a math operation, so the sign is reversed, so K equals -2. The center of this ellipse is going to be at 6, -2. All right, I suppose we could sketch this thing, right? 1, 2, 3, 4, 5, 6. 1, 2. So the center of our ellipse is going to be right about there. All right. Now, this number is bigger. This is telling us how wide it's going to be. Because the number under the X binomial is bigger, that's telling us our semi-major axis is in the X direction. So this is going to tell us A. And if we could just take a moment to revisit these equations. Notice these are A squared and B squared. They're asking for A and B. So we need to take the square root of these numbers. So the square root of 9 is 3. That means we're going to go 1, 2, 3. 1, 2, 3. There's the width of our ellipse. B is the square root of the smaller denominator. So this is 2. So we're going to go 1, 2, 1, 2. And there's our ellipse. All right, so here is your center. And then A is whichever one of these is bigger, it's that one. Take the square root. B is whichever one of these is smaller, take the square root. Wonderful. All right, let's go do another easy one. You go, oh, easy, Barton. Barton, it's not a fraction, please. Chill. Breathe, but not so fast. Okay? Calm yoga breaths. 3 seconds in, 6 seconds out. All right, you ready to do some math? The first thing you're freaking out about is there's no fraction here. So we're going to turn it into a fraction. What invisible number do we divide by that won't change the value of anything? Tell your dog Pablo. 1. There you go. Now it's a fraction. Now you don't have to freak out. You're fine, kid. See, I told you you're going to be fine. You're fine. Don't worry. All right, so let's find our center. So our center, here's X. So that means this thing's H, but we have to change the sign. So this is +9. So we're at 9. Here's K. It's inside an operation. Change the sign. K is 4. So our ellipse is going to be at 9, 4. That's the center of our ellipse. All right. Now we need to find A and B. Remember, A is always the bigger number. What's bigger, 25 or 1? 1. No, the other one. 25. All right, good. So take the square root of the bigger number. Square root of 25 is 5. That means A is 5. Take the square root of the smaller number. B is 1. So what that means is, oops, I'm going to need a lot more room than that, right? So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. my Spanish knowledge of numbers ends at DS. All right. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Oh man, you can tell that my horizontal axis is a little less compressed than my vertical, but c'est la vie. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4. That means because the larger number is under the y, we go 5 in the y direction. 1, 2, 3, 4, 5. Let's see, about that same distance up, right about there. There we go. And then our horizontal axis is 1. So we go left 1, right 1. So we have very tall, skinny ellipse. There you go. That's your ellipse from this one. All right, not so bad. All right, now we talked about foreshadowing. I said something like the easy version, the easy form. So you're right, like, you guys, I can't just let you leave doing easy stuff your whole life, right? I understand difficult things are difficult, but that's what sets us apart from dolphins and dogs and grasshoppers, right? We sit down and voluntarily, I'm not here voluntarily, Barton. Yeah, I understand, but we sit down and voluntarily subject ourselves to grueling mental exhaustion for our personal growth. Okay? Don't think of it as hurting your brain. Think of it as growing as a person. All right, let's do a hard one. And now, I already know what you're thinking. You see this thing and you go, oh, sweet mother of Jove, oh, Barton, God bless America. Holy Jesus, Mary, Joseph, and St. Peter, I know what you're thinking, you guys. Here, you want to see a picture of you guys? That's you. That's so funny. Oh, that's you guys right now. It's all right. We'll make it better. All right. So this is like when the circles are written in standard form. This is standard form, not nice vertex axis form. So we need to turn this thing into this so that we can figure out where's the center, how wide is our ellipse, and how tall is our ellipse. So just like we did with circles, we're going to group the x terms, we're going to group the y terms, and we're going to do some completing the square. So I watched another guy teach this. You're going to have to excuse me, but I forgot his name. I know you should always cite your sources, but I'm sorry, I forgot. So I saw this trick that might make this a little easier. What we're going to do is we're going to move this term over to start with. So what I'm going to do in this step is I'm going to group my x's and my y's together, and I'm going to move the 16 over by subtracting 16 on both sides. All right? So we have 16x squared minus 32x plus y squared plus 50y equals negative 16. All right, so now we have to complete the square on the x's and on the y's. When you do that, you definitely don't want to have your this coefficient in front of the squared term. So what we're going to do first is we're going to take out the GCF of the x's and of the y's to make this problem a little more digestible for us. So the common factor here is 16. So we're going to factor a 16 out of our x's. So we'll put 16 x squared, because 16 goes into 16 one time. 16 goes into negative 32 negative 2 times. And I'm going to put a little plus blank here, because we're going to have to fill that in a second. Okay. For the y's, our common factor is 25. So we're going to put plus 25. Y squared plus 25 goes into 50 twice. 2y plus blank equals negative 16. Let me scoot this over so we can see a little bit better. There we go. So it's not quite so smushed. All right. So let's complete the square on this, and then we'll come back and fill in these blanks, because you kind of have to do the factoring first to know what goes here, but we'll live. So bring down your 16 so you don't forget it. All right. Here, this will factor to the same thing every time. There's a pattern. It's going to be x and then something squared. To get this something that goes right here, it's just half of this right here, half of the linear term. So half of negative 2 is negative 1, so we're going to have minus 1. Perfect. Now to get the number that goes in here, we have to square this number. So negative 1 squared is positive 1. Let me put that in purple. Plus 1. Perfect. Let's come look at the blue part. So I'm going to bring down my plus 25. Great. Now, here, same process. It's going to be y something squared. To get this something, it's still half of the linear term. So half of positive 2 is positive 1. And then the number we put in here is this number squared. So 1 squared is 1 again. All right, so we're almost there. Not quite, almost. All right, so now I've just added 1 here, but this 1 is not really going to stay a 1. If I wanted this whole thing to factor, I've taken this 16 out. So because of this 16 here, if I wanted to simplify this 1, I'm not just adding 1. I'm adding 1 times this coefficient. So I'm adding 16 to this side of the equation, correct? So let's see, sorry, that's a negative. Okay. So what we're going to do is we are going to add 16 to this side. Because I just added 16, 1 times 16 is 16. Because I added 16 on this side, I have to do that on this side of the equation also to keep it balanced. So plus 16. Here, I've added 1, but this isn't going to stay a 1 because it's going to get multiplied to the 25. So this is actually 25 that we're adding on this side. So if I add 25 on the left side of the equation, we have to add 25 on this side of the equation as well. All right, now we are going to simplify this side. So negative 16 plus 16 is 0. They cancel each other out. And then we just have 25 left over there. Perfect. All right. Now, we're almost there, right? We've got our binomial squared plus our other binomial squared. Now, all we need to do is make this equal 1. So what we're going to do is we're going to divide both sides by this number. So when you divide both sides, you have to divide the whole side. So we're going to divide that by 25 and this term by 25. Great. All right, so when we do that, sorry, give me one moment. Sorry there. My wife was trying to get my attention. She didn't talk to me for half a second. Pardon the interruption. All right, so like I said, this number needs to be a 1, so we're dividing both sides by 25. All right, 25 over 25 is 1, just like we want. Here, 25 over 25 is 1. They cancel out. So we have plus y plus 1 squared. And here, 16 over 25 doesn't really cancel. So you could leave it this way, but that makes finding your a term a little bit fishy, right? Because our formula is not a coefficient on top and a number on the bottom. It's just a number on the bottom. So we need to bring the 16 down here. And the way you do that is you're going to just put it underneath the 25. All right. So this is x minus 1 squared over 25 over 16. I understand that this looks ugly as heck, but that's kind of the way you would want to do it. That's why most people would probably leave it this way. What this is telling you is that your a is a fraction. If you take the square root of this, this is 5 over 4. So that's a. A is 1.2. The problem here is that your semi-major axis is a decimal in this example. Sorry, I don't know. I don't know what you want me to say. Sorry, decimals exist, I guess. Oh, Barton, you know my 3 greatest. Yeah, I know the spiel. All right, so that would tell us that our final equation for our ellipse. Come on, you son of a gun. All right, so the final equation for our ellipse is going to be x minus 1 squared over, if you want, you could do whatever 1.2 squared is. I think it's 1.44. That's kind of bad math. Most mathematicians kind of just threw up in their mouth a bit because you don't want decimals in fractions. Scientists are like, sweet, a decimal. Engineers couldn't be more thrilled. Mathematicians puked a little bit. Because I like to pretend I'm a mathematician, I'm going to leave it as a fraction. 25 over 16 plus y plus 1 squared over, again, we don't have anything, so you could put a 1 if it makes you happy, equals 1. Now, let's go answer the question, right? We did all this crazy work. What's the question? Our question is, where is the center? Where's the or how big is the semi-major axis, and how big is the semi-minor axis? So our center, here's h, so h equals 1, k equals -1. So our center is going to be at 1, -1. A is the bigger of these two numbers. So what's bigger, 25 over 16 or 1? Well, the top's bigger here, so this is bigger than 1. So square root, a is 5 over 4. B is the square root of the smaller number. Square root of 1 is 1. And then there is your center, your semi-major axis, and your semi-minor axis. All right, now that you're thoroughly scared to death, go ahead, hop back in the WebEx, tell me how scared to death you are of ellipses. I can do another example or go over some homework questions with you. If you're not scared to death, congratulations, you're not scared. You're not cool. You're not tough. Nah, you might be tough. I don't know. All right, have a good day, you guys.